Welcome to Symmetry, Structure, and Tensor Properties Materials, Lecture 21. We've just completed P4, which was a natural follow-on to P2. And now we are going to move on to P3 and P6. And again, just using our same new combination theorem. But since P3 and P6, you can imagine, are somewhat related, we'll do those together. So here's P3. Again, I'm using our group theory to help us understand what's going on. And so we have our point groups. P3 point group is identity, and then 120, 240 degrees. And here's our theorem, you recall, that allows us to pick out where we have other rotational elements, even though we're not focusing on them initially. So let's do out this threefold axis. Remember how we have something in the primitive cell case for threefold axis that I'm going to try to draw this well here to be sure that we end up with something that looks like I have 60 degrees and 120 degrees around these. So that's what I'm trying to do. So you recall, in this case, the translation vectors look like this. There's 120 degrees here. And same over here, and then we'll call, oh geez. So here we have our P3 point group with the identity element and 120 degrees and 240 degrees, and then our new theorem that said that when I put a point group from a rotation onto a point inside a lattice with T1, I end up with other equivalent symmetry elements, rotations, somewhere else. So let's draw our P3 lattice. We had shown that in the case of the primitive lattice here, compatible with threefold axis, remember we had 120 degrees here, right? And of course, by definition, we're saying we have threefold axes here. We draw this diagonal for convenience typically. Of course, it's a real translation vector as well. And so now we want to look at our theorem. Well, we have the new elements that we haven't looked at yet. Because remember, we've looked at other angles with translation vectors. We don't need to repeat those, but here we haven't looked at 2 pi over 3 yet. So a priori, we can't just say, oh, I know what that's going to be. But we're going to end up with that new rotation of 2 pi over 3 because remember, it's the same as the alpha of A. And it's good, but it's going to be located at x equals t over 2 cotan 2 pi over 3. So that equals 0.5774, which we all know is also 1 over the square root of 3 t over 2. So let's come over here and look at that. So here's our t over 2 if we use this particular perpendicular bisector. And remember, x is some distance along here, and we've just said that x equals 1 square root of 3 t over 2, and what you'll see if you work out the math, because remember the 60 degrees, I can drop this here. Remember how in a 30-60 triangle, which would be 30, 60, they're all related by things like the square root of 2, so that's square root of 3. So it won't surprise you that 1 over square root of 3 t over 2, which is, remember this one, is this here. And so we end up right in sort of the middle of this guy. And so then we would construct a new threefold axis. And of course you'd have one here because there's a bisector there, there's a bisector there. So you end up with these two threefold axes, which we might not have seen upon inspection. So what that means is that you'll be able to see this by drawing in our little motif. So imagine that I have a motif here. Hopefully you can convince yourself by looking at these red ones that we have a threefold, motif hanging on each one of these. And you can see now how, if I look at this guy especially, this guy rotates into this guy, rotates into this guy, rotates into this guy. So as before, we have, remember with the P4, we have sort of a tilted relationship here of these motifs, because I drew them off of the point, which I should to show the general nature of things. And you can see here that, that there indeed is a threefold axis in there. And so we have P3. Now, again, since we've done all this, we don't need to think now too hard about P6, and we only have to add one more angle. So let's go on and think about P6. So for the P6, symmetry, we have our six-fold point group. Now, I should have written the previous one. I used that P notation again like I had on the other one that I erased before. That, the proper notation is not P, it's these brackets which denote N, where N is six-fold, right, point group. And so that's just representing our, another way of writing that, if you recall. That's our symbol, and that's the writing out. We write it out this way in the group theory. And we've already done A over pi, we've already done, because we did the P3, we've already done inserting these two angles using this theorem, right? So now the only new one we have to consider is the smallest new angle for a six-fold axis, which is 60 degrees. So let's write out all the ones that we already know, and then we'll do that one last. And recall that the reason that we draw the standard cell this way and not centered is because we have the special case. These are isosceles triangles with 60 degrees, and that the whole thing is 120 degrees. And we have six-fold at each one of these lattice points. So what it means, what this point group means, is even though the highest symmetry, we think about it as 60 degrees each angle, remember in there we can choose compatible with that. It could be, I could do double a 60 degree rotation, which would be 120 degrees. We've already done that case. You can think about having in this six-fold axis, then it also contains elements of the triangle, which we've already done. And we learned that if we have two triangles like this, the bisector produces that square root over 3 up, 1 over square root 3 up, that 1 over square root 3t over 2, you end up with triangles. And so that was from these guys. And then recall, if we go back to P2, you can also think about having two fold axes in here, right? And so that meant there's two fold axes at all of the bisectors between all the two-fold axes, if we choose to look at it that way. So all that we need left then is to think about the 60 degree, and remember that any additional symmetries we can't see right off the bat in this case are going to come from so solving for that is really square root of 3 times t2, but I purposely wrote it this way because by inspection then you can see that if we now think about these hexagons with the smallest rotation, look at the place in between. Recall our theorem says the other angle is going to appear on this line, which is bisecting the two endpoints, lattice points with the hexagons on them. And we're going to be square root of 3 over t up. Now remember, what we have here, this is 30, this is 60, this is 90. So we have a 30-60 angle triangle, which means this is t, and we knew from before that this is t over 2. And then this whole thing is square root of 3 over 2t. So that means that if I go up this amount, it actually inserts a hexagon where there's already a hexagon. And so we find out that in the case of P6, the only changes over P3 are that we have an A pi element which induces these guys in there, and we didn't have that in the case of the P3. And that's it, because the other smallest angle actually just induces, if I have a bisector between these two hexagons, it just induces another hexagon when there is already one. And that's P6.